Hello all, welcome back to my channel. So today we will be doing a comparison of all the sorting algorithms which we have learned in the previous sessions. So sorting algorithms in a nutshell. So this video is going to help you all in case of an examination during which if you want to quickly go through the working of an algorithm, what is the different time complexity of the algorithm, all those things. If you need a quick reference, that is going to be helpful. So I'll try to make it as short as possible. So in the previous sessions, we have already covered merge sort, quick sort, selection sort, bubble sort, insertion sort, and shell sort. All these six algorithms for sorting has been explained elaborated way with the help of an example. So I request you to kindly go through that. So now in today's session, we will just quickly run through it to understand and recall the working of them. First, let us see that why sorting matters. Why do we require sorting? And why we need to learn that. Now, sorting, as we have seen in the previous session also, it is nothing but organizing the data. Why do we need to organize? It is for efficiency. So, sorting transforms unorganized data into structured format, making it significantly faster and easier to search, process, and retrieve specific information. Okay, so if it is in certain organized way, for example, if we are organizing our books, organizing our clothes, it is going to help us in the next day. Isn't it? In a similar way, if we are organizing the data, that is going to help us make our other work faster. That is the reason we use these algorithms. Now, apart from that, it also enhances real world applications from optimizing database queries to improving search engine performance, enabling the efficient AI algorithm sorting is a foundational process across diverse computing domains. So, that is a significance. That is why sorting matters. That's the reason we have learned all the different kinds of sorting algorithm, which will be used depending on their usability in different places. Okay, so in today's session, we will cover all these six algorithm which have been discussed in an elaborated way. So let us go through them one by one. The very first algorithm is bubble sort. Now, how does a bubble sort work? Suppose I have a array like this. What I'm going to do is I'm going to compare the two elements and I'm going to see now. I'm going to compare and see if they are in a proper order. As you can see, 5 is greater and 1 is lesser, which means it is not in a proper order. I'm going to swap it. So after swapping, 1 is going to come here, 5 is going to come here. Now I am going to compare the next two elements, that is 5 and 4. Once I'm comparing, I'm finding out that this also need to be swapped. So I'm going to swap. As you can see, this has come here. I'm going to compare the next two elements. Similarly, I'm going to compare. Now, once I complete the comparison, once I have come to the end, this is called as a first pass. Similarly, I'm going to do second pass, third pass until I'm going to do no more swaps. I will be continuing the bubble sort. So here the concept is the bigger element always bubbles down to the last element. So every time after every pass, as you can see, 8 has reached its correct position. In the second pass, 8 and 5 has reached its correct position. Similarly, it will go on happening like that. That is the name. That's why the name bubble sort. So this was a working of a bubble sort. I hope it is. I hope you all remember it. So what does it do? It repeatedly compares two adjacent elements, and if they are in a wrong order, they will swap it. This process continues until the largest elements bubble up to the top of the list. Okay. So what is the complexity? The best complexity is order of n. Average complexity and the worst complexity is order of n square. Okay. So this is the complexity. This has been also discussed in the previous session. So remembering the complexity is also important. Next we have is a selection sort. In selection sort, what we are going to do is I'm going to find out the minimum, the smallest element, and then I'm going to place it in the beginning of the array. So once I place that, I'm going to consider that this particular place is sorted. Now I will start from here. I will start comparing or find the minimum next element, and then I'm going to place it again in the beginning. Now this is sorted. I'm going to only look at the remaining part of the array. Find the minimum element here. I have found 10 and then place it. So similarly, I'm going to continue through all the array. I hope you can recall now. Okay, so this is the working. So selection sort improves upon the bubble sort, okay, by reducing the number of swaps. because we are trying to find out the minimum, instead of comparing each and every element, neighboring element, we are only checking for the minimum and then we are selecting the particular minimum and then doing the sorting. That is what is selection sort. It iterates through the list, finds the minimum element from the unsorted part and place it at the beginning of the sorted part. Okay. Here the best case, worst case, and the average case remain same. It is all order of n squared. So that is your selection sort. So the next algorithm is insertion sort. Now, as the name says, it is insertion sort. We are going to insert the element based on their places. Okay, so in this, the very first element, I will be considering it as a um, sorted element. Now I'm going to compare it with the next value, but I'm finding that this element is smaller than this, which means I'm going to now insert this new value over to its correct position, and I will shift the initially what value I took it as a sorted value to the, that is simply I'm going to exchange the value. So as you can see, the value has been exchanged. Next, once again, I'm going to compare. Now this is, I am assuming this has reached its correct position. Now I'm going to compare these two. When I'm comparing these two, once again, I'm finding that this is greater than this. Once again, the switch happens. As you can see, these two are in the correct, these two have been moved before 23. Now I'm going to compare the next element with all these. Now remember, unlike where we had selection sort, where we found the minimum element and then we inserted, this is insertion sort. So what I'm going to do is I'm going to find the element. Next, I'm going to check whether it is greater than or less than 23. So in this case, it is greater. Of course, then I have to next compare the next element. Next, I will check whether it is greater than or less than the 10. Now, of course, it is less, so which means I need to check the next element. Once again, I will check if 5 is greater than or less than 1. Now, when I'm comparing, I find out that it is less than 1, which means somewhere here between is the position of 5. So, hence, I'm going to insert it over here. Hence, the name insertion sort. The next element left is 2. 2, once again, I will compare it with 23, which is smaller than 23. Again, I will compare it with 10, which is smaller. Again, I will compare it with 5. It is smaller than 2 as well. Sorry, 5 as well. Next, I'll compare 2 with 1, but it is smaller. Once again, I know that position is somewhere over here, and hence it is inserted over here. Okay, so this is how insertion sort work. I hope it is clear. Now, bubbles working off a bubble sort, selection sort, and insertion sort, they are entirely different. Okay, as the name says, here we are finding the position and inserting it just like how we do the while we are playing the card. The insertion sort builds the final sorted array one item at a time. It iterates through the input elements and inserts each element into its correct position in the already sorted part of the array. So efficiency for small or nearly sorted data with the best case time complexity of order of n, and the worst case is order of n square. This is what the time complexity of insertion sort is. And the next algorithm what we learned is shell sort. Now shell sort is once again a very algorithm. Here we work on the basis of a concept of something called as a gap. So initially we will take a certain value as a gap. So in this particular example, we have taken 3 as a gap. So what we are going to do is I will take the first element and 1, 2, 3, and I will compare this element. Similarly, I will take 1 and I will compare 4. And similarly, I will take 23 and I will compare 9. So basically what is happening is I'm going to compare the elements only which are having a gap 3. So once I compare that, this is what I'm going to get. Okay, so when I compared 10 and 50, I know that 50 is greater than 10, so there is no swap. When I compared 1 and 4 also, I know that 1 is smaller and 4 is greater, hence it is in a correct position, no swap. When I'm comparing 23 and 9, I realize that 23 and 9 is smaller, hence as you can see, there is a swap here. So once I do that, once I complete with the 3, next I'm going to reduce the gap and I will start with 1. So which means, so initially, suppose if you're starting with the gap 7, then you will reduce it to probably 5. It depends. Either you can do -2 or you can do divide by 2. If you're doing divide by 2, then your next gap will be 3 and then your next gap is 1. So whatever the value of the gap you're taking, the moment you come for 1, it is going to be like a insertion sort. Okay, so we will compare and Similarly, simultaneously, you are going to swap. So in this case, by the time you complete all this comparison and swapping, you will reach to your sorted list. So that is how your shell sort works. When it comes to the shell sort, you should remember the concept of gaps. Okay, so shell sort is an extension of insertion sort designed to improve its performance. It sorts elements that are far apart from each other by creating gaps, then progressively reduces the gap size until it becomes one, which is essentially insertion sort, like I told you. So, what about the complexity? So, much faster than basic insertion sort with an approximate time complexity of order of n square, order of n log n, or order of n to the power 3 by 2, depending on the gap sequence. So, here choosing the gap becomes very crucial. And the best case is order of n log n, and worst case is order of n square. Okay, so this is how your shell sort works. Next comes is our merge sort. Now, merge sort, as we all know, that what we are going to do is we will take a middle value, and then this is basically works on a concept of divide and conquer. We are going to divide the array until we reach a single element. The moment we reach a single element, then we are going to start the merging of the array. So when we are merging, we are going to merge in a way that we are going to get a new array which is sorted. So as you can see here, 6 comes first, 42 comes next, 2 comes first, 32 comes next. Here, as you can see, 8 has been merged first, and then 15, 4, 23. So when you see that, when we start merging, it is in a sorted way. Next, again, we will merge these two. As in this and this, when I'm merging, once again, I will compare the elements and I will merge it in a way that that is a sorted array. And the final array is also merged, and this also we will be getting a sorted array. So this is the concept of merge sort, which is purely divide and conquer method. So merge sort is a highly efficient comparison based sorting algorithm that follows the divide and conquer strategy. It divides the unsorted list into n sublists, each containing one element, and then repeatedly merges the sublist to provide new sorted sublist until there is only one sublist remaining. That is a final array. Okay. So complexity known for its consistent order of n log n time complexity in all the worst, average, and the best cases. Okay. So this is one of the best algorithms when it comes to sorting. And the last algorithm we discussed was quicksort. In quicksort, also we will divide the array, but here we will see the concept of pivot element. So we'll take one element as a pivot element, and we will arrange the array in a way that the pivot element is it reaches its correct position. So similarly, we are going to divide until the pivot value reaches its correct position, and then we are going to merge it. So when we merge that, we will have all the elements in its correct position, and hence our array is sorted. Okay. So quick sort is another highly efficient comparison based sorting algorithm that is also uses a divide and conquer strategy. It picks an element as a pivot and partitions the array around the picked pivot such that all smaller elements come before the pivot and all the greater elements come after the pivot. So by when we do that, we know that the pivot has reached its correct position. So similarly, we'll go on dividing the array and finding a new pivot, and hence all our elements get sorted. An average case complexity is order of n log n, making it very fast in practice. However, worst case is order of n square. Okay, so this is the complexity of our quicksort. So that is how our six algorithm which we have discussed previously. Briefly, I explained the working of it. So this is the table, the same working in a tabular form. This you can quickly refer during your examination. How does the bubble sort work? Selection sort, insertion sort, merge sort, quick sort, and shell sort works. Also, if you want to remember, okay, so bubble sort, you can understand it as like arranging books by swapping the neighbors. And you have to imagine that the thicker book, you're going to bring it down as and when you're comparing. Selection sort is like picking the smallest card each time. So you're going to select the smallest element and then you are going to place it in its position. Insertion sort is just like you have a random cards with you, but you need to arrange it in its sorting value as in ascending order. Then how are you going to insert it? Merge sort, for that you can remember it as divide and conquer strategy. What is quick sort? Quick sort is like organizing number around a chosen reference. This reference is nothing but pivot value. So you have to think about a pivot value and then you will arrange rest of the things around it. Okay, so here also we will use the divide and conquer method. And last, shell sort, it's like sorting in layers until refined. So here you can think about a gap when it comes to shell sort. So we will compare only between only to those gaps and we'll reduce the gap until we are reaching a single element and then we'll apply the insertion sort. Okay, so you can refer this table for a quick reference. Also, this is also a table where I have summarized all the best, average, and worst cases of all these six algorithms. Also, I have mentioned the space complexity. Now, the space complexity is nothing but the space used by that particular algorithm. As you can see that it is constant when it comes to the bubble sort, selection sort, insertion sort, and shell sort. When it comes to the merge sort, it depends on n, so it is order of n, and it is quick sort, it is order of log n. So this is the best space complexity compared to other algorithms. All right. I hope this particular video will help you as a quick reference. In case if you need any other kind of a videos, kindly put it in a comment box. I'll try to bring it to you. Till then, keep watching, keep learning. Thank you, students.